In this video, we'll cover general planar motion with telescoping or radial motion. I'll start by breaking it down. It consists of translation, plus rotation about a fixed axis, plus telescoping or radial motion. And we'll put them all together and analyze the motion of point B with respect to an inertial or earth fixed reference frame. To do this, we will need our inertial reference frame. Then we can define the position of point A using dimensions x and y. It will also help to add a rotating reference frame fixed in the rod with its origin at point A. Then we can define the position of point B with respect to A using the dimension r. Before we go on, you should be aware that the book also defines two reference frames. Capital XYZ is the inertial reference frame, and lowercase xyz is the rotating frame. You should feel free to use this notation, but I'm concerned that it's not always easy to distinguish between capital XYZ and lowercase xyz. Moreover, there may be times when you need more than two reference frames, and so for all of these reasons, defining reference frames with different letters can work a bit better. So, let's say you want to find the velocity of b with respect to e. We can use this equation. It's equation 1626 from the book. Be aware that for this equation to work, A must be a rotating reference frame, and it typically has one unit vector or coordinate that passes through the point of interest. Also be aware that the book uses capital omega to indicate the rotation of one reference frame with respect to another, and lowercase omega to indicate the rotation of a rigid body. However, many times people don't make a distinction between capital omega and lowercase omega. Very often, they just use lowercase omega to indicate rotation in general, and then they use the subscripts to indicate what is rotating with respect to what. Because you can easily fix a reference frame in any rigid body, the difference is minimal as long as you define your subscripts appropriately. So to use the velocity equation, just realize that the velocity of A with respect to E refers to the translation of point A as seen from the E reference frame. The velocity of b with respect to a refers to the telescoping motion. Be careful with this. Students often find it confusing, so make sure you understand why this is r dot a1. If you don't see it, then think of yourself sitting at point A, rotating with point A, and looking out toward ball B. You would always describe ball B as being in front of you along the A1 axis, and you would describe it as moving in and out at a rate of r dot with no motion from side to side. So next, capital omega refers to the angular velocity of the rigid body and typically has a magnitude of theta dot. And the position of B with respect to A is the radial position of point B with respect to A. Let's do one more thing. Let's plug in the expressions into the velocity equation and take the cross product. Notice now that we have velocity terms related to each type of motion. We have translation, radial motion, and rotation. Now I'm going to shrink the picture to make some more room. And let's say we want to find the linear acceleration of point B as seen from the E reference frame. We can use equation 1629 from the book. It looks long and intimidating, but we'll break it down. It's really not that cumbersome to use. Here again, A refers to a rotating reference frame. Capital omega is the angular velocity of the rotating reference frame with respect to the inertial frame, and omega dot is the angular acceleration of the rotating reference frame. In this case, the acceleration of A with respect to E refers to the linear acceleration of point A as seen from reference frame E. The acceleration of B with respect to A refers to the linear acceleration related to the telescoping motion. Omega dot is the angular acceleration, and the rest are the same as before. If we plug these expressions into the acceleration equation and then take the cross products, noting that A3 cross A1 is A2 and A3 cross A2 is negative A1, and then collect terms, We note that we have terms representing a number of acceleration components. These include translation, radial motion or telescoping, centripetal acceleration, linear acceleration due to rotation, and Coriolis acceleration. Coriolis acceleration is the most difficult to conceptualize. It has to do with the fact that different points along the radius of a rotating rigid body have different linear velocities. So, if an object like ball B is moving away from the axis of rotation, then its linear velocity must increase in the transverse or A2 direction simply because its distance from the axis of rotation is increasing. So to summarize, equations 1626 and 1629 in the book are meant to be applied in situations when there is general planar motion with telescoping. The idea is that assuming you know the positions, velocities, and angular velocities specified, you can find the linear velocity and acceleration of point B. As we covered previously, there are other equations that apply in situations when there is only general planar motion and rotation about a fixed axis. However, note that the equations for general planar motion are simply the ones for general planar motion with telescoping, but with the telescoping term set to zero. Similarly, the equations for rotation about a fixed axis are the same as for general planar motion, but with the translation terms set to zero. So if you're in doubt, start with the most complicated equations for general planar motion with telescoping, and then substitute the terms with zeros as appropriate. So let's do an example. The bridge is rotating with a constant angular speed while a man runs along the road. We're asked to find his velocity and acceleration when he's 15 feet from the center of the bridge. If you do this by the book, then you will see that there are already x, y, and z coordinates drawn in the bridge. What you don't see is another coordinate system, capital X, Y, and Z, fixed in the earth. Just so there's no confusion, I'm going to add a rotating reference frame fixed in the bridge with origin O, such that unit vector O1 is along the man's radial path of motion. I will also add an earth fixed reference frame that aligns with the O unit vectors when the bridge is closed. Note also that the angular velocity vector is oriented in the O3 direction, which is equivalent to the E3 direction. Now we need to think about the types of motion that are occurring. You might be tempted to say that this is general planar motion because the man is translating and the bridge is rotating. However, in this case, the bridge is the rigid body. It's rotating but not translating. And the man is contributing telescopic or radial motion. So to find the velocity of the man as seen from the E reference frame, we'll use equation 1626. But as always, we'll need to change the subscripts to suit this particular problem. I'll refer to the man as M. He replaces B in the equation. And the axis of rotation passes through point O. It will replace A in the equation. Now we need to write down what we know. The linear velocity of the bridge is 0 feet per second. The angular velocity of the bridge is 0.5 radians per second in the O3 direction, but it's always a good idea to write expressions for the vectors in terms of variables. This will allow us to write equations for the motion over a long period of time, which is much more useful than finding velocity or acceleration at just one instant. So we'll call the angular velocity of the bridge omega O3. The position of the man at the moment of interest is given by d, and it's 15 feet in the O1 direction. The velocity of the man with respect to O is d dot, or 5 feet per second O1. And now we can substitute, and we obtain our expression for the motion over a long period of time. And now we can plug in values and do the calculations, and we arrive at a velocity vector at the moment of interest. And now we can do the same thing with acceleration. We start with equation 1629, which applies to general planar motion with telescoping. We change the subscripts of the equation to fit this problem. We identify what we know, In addition to the variables we already identified, we can say that all of the linear and angular accelerations are zero, since the velocities given are constant. Then we substitute the variables and simplify, and then plug in values and calculate, and we get our answer. Before we close, let's reset this problem and work it a different way. You might occasionally hear me say that although it's often more convenient to work with rotating reference frames, you can always work problems using only the Earth fixed unit vectors. I also said that the radial motion equations require A to be a rotating reference frame, so that seems contradictory. And in fact, you do get somewhat stuck when you try to write an expression for the velocity of B with respect to A and the acceleration of B with respect to A using only the inertial reference frame. It's a little tricky. But remember, we can always use the basic kinematic equations. So let's try working the problem starting with those. And I'll start with velocity. I'll rewrite equation 1 with the appropriate subscripts for this problem. And now we need to write an expression for the position of the man with respect to E. This is a little tricky, but let's start by realizing that we can use vector addition to write the position of the man with respect to E is the position of O with respect to E plus the position of the man with respect to O. Then, since O is rotating with respect to the inertial reference frame but not translating, we can just say that the derivative of the position of O with respect to E with respect to time is just 0. So now we just need an expression for the position of the man with respect to O. To help with this, let's redraw the inertial reference frame as if we were looking down on it. And then let's add the man's path. You might take issue with the way I've drawn theta. The picture makes it look like theta should be going the other way, but look at the angular speed arrow. It is positive in the counterclockwise direction, which is also the direction of increasing theta. Hence, the angle shown must be a negative value of theta. So based on the diagram, the position of the man with respect to O is d times the quantity cosine theta E1 plus sine theta E2. Be careful taking the time derivative. Remember that d dot is not 0. And then collect terms. It looks like we need a value for theta here. So let's just assume that theta is 0 radians. And in fact, in this case, you will get the correct magnitude for any value of theta. Plugging in values now, remembering that theta dot is just the angular speed. And we see that the magnitude of the velocity is the same as before. For acceleration, we start with the expression for the velocity we just found. Make sure to use the expression with the variable so we don't accidentally assume a value is constant when it isn't. Then we use kinematic equation 2 and take the derivative of the velocity expression. This is fairly cumbersome, but certainly not impossible. Then again, we will assume that theta is 0. But be careful when you're doing the homework. Very often you'll be given a non-zero value of theta. Collecting terms now, we get a much smaller expression. And then plugging in values, noting that d dot and theta double dot are both 0, we get an answer with the same magnitude as before.